Namaskar. Welcome to Prakash on Basics. I'm Prakash Zo. We've been talking about energy all along. Uh, but if you look at the universe, it's made out of energy and matter. Of course, along with temperature and time as the two other controlling factors. So it is this matter that we see all around us, right from the microscopic organisms to the black holes and the galaxies and everything else. All life is nothing but matter that we see around. What we interact with is matter. And the base of all this matter is atoms. So it is these atoms that we must understand properly to understand many of the phenomena that are around us. They are the building blocks of everything around us. So if we understand the structure, the size, the nature, the properties of atoms, we can understand practically everything that is around us. Most of the physical and chemical properties that we talk of are all associated with these atoms. Every element that is around us has its own characteristic atom. The combination of these atoms results into either molecules or compounds that are all around us. These stable combinations are known as molecules. All metals are nothing but atoms, and all gases are all molecules. And every material that we have, including me, my body, everything around us, all this is nothing but atoms and molecules put together. The universe itself began with two of the basic atoms, hydrogen and helium. These were the first two elements that we always talk of. The oxygen that we breathe is a molecule made out of two atoms of oxygen. And the carbon dioxide is carbon plus oxygen, that is three atoms put together. And ammonia is NH3, that is one nitrogen and three hydrogen, that makes it four. And methane is CH4, which is carbon plus four hydrogen. So everything, one, two, three, four, everything, and this will continue till we talk of our genetic code and hemoglobin and so many other things. And these are extremely complex molecules, but they are all finally made out of atoms. So let us try and understand what these atoms are. Kanad, the guru of Vaisheshika philosophy that we will discuss sometime, proposed the concept of these basic particles which form everything. This was around 600 BC, 6th century BC. He called it the Paramanu, the smallest undivisible particle. But the word atom that we use is a later coined word from Greek terms. And there were a lot of experiments that were carried out to study these atoms in the last 200 years. People like Dalton and J.J. Thomson and Rutherford and Bohr and Sommerfeld carried out a number of experiments that came up with the theory, the original basic theory of what atoms are. They developed the structure of the atom. Today, of course, it's a far more complex situation. But let us try and understand this basic model of what the atom is. There are a number of beautiful experiments that were carried out, but we'll talk of those experiments later on. Today, we'll only try and understand what the atom is. The atom consists of a nucleus, that is a central core, and orbiting around it are electrons. This is not in one single plane like the planetary system as people talk of. It's actually a three-dimensional situation. It keeps on winding in all possible directions. The electron keeps on turning around. The nucleus is positively charged because of the protons that are there inside. Each proton has a charge. I'm going to talk about a number of numbers and their powers today. I don't want you to remember these numbers, but if I talk of the order of magnitude, that is the power of tens, you will be able to understand how big or how small these numbers are. It is only understanding the size that is more important. The proton has a charge of plus positive charge 1.6 into 10 raised to minus 19. That means 0.18 zeros and 1 6. It's extremely small. How it was measured is a beautiful experiment that we will talk of sometime later. Then there are, along with the protons, there are neutrons within the nucleus. They don't have any charge. And the electrons, which are negative, that has again the same charge as the proton, uh, but negative, minus 1.6 into 10 raised to minus 19 coulomb. And this was calculated by a person called Millikan using an oil drop experiment. Again, sometime later. These electrons keep going around. But how many electrons? Different atoms have of different elements have different number of protons and neutrons. The number of protons is known as the atomic number, and the number of protons is usually equal to the number of electrons in a normal neutral atom. How many elements are there? As of today, we talk of around 118 elements, a very large number. We don't use all of them every time. Uh, Up to calcium, which has an atomic number of around 20, the number of protons and neutrons is identical. But later on, in order to make the whole system stable, the number of neutrons starts building up. By the time you come to an element known as lead, it has 82 protons and 207 neutrons. Everything beyond lead is radioactive, and that's a completely different area, not for today. Uranium, for example, has 92 protons and 238 neutrons. But sometimes this number of neutrons could be different. It could be 235 or 237, and such variations result into what are known as isotopes. We know that ozone is an isotope of oxygen. We know carbon 14 that I'll discuss sometime. And uranium, some are used as fuel and so forth. Uranium 235 and 238 and so forth. So all these numbers are associated with what that atom is. The name of the atom is given by the name or the number of the protons or the atomic number that is present. All these atoms are now arranged in an order. A Russian scientist known as Mendeleev first did all this, and it is known as the Mendeleev's periodic table. Not a part of common understanding right now, but realize that they've all been organized properly, and everything is there based on the number of protons. So, what holds the nucleus together? There are a number of forces in nature. I'll go into details sometime later, but today I'll just mention what these forces are. The one that we always know is the gravitational force. But, friends, that is the weakest of all the forces. Then comes the electrostatic force. That is the force between any positive and a negative charged particle. This electrostatic force is 10 raised to 38 times stronger than the gravitational force. If we talk of two protons, if I take two protons and find out how much electrostatic force of repulsion is there between them and how much of gravitational force is there, 10 raised to 38 means 1 followed by 38 zeros is the value by which this force is effective. In some calculations, it is taken to be close. If you take into other account some other variations, it is around 10 raised to 36. And that is very large as compared to the gravitational force. Then what about the nucleus itself? Within the nucleus, there are two forces: weak nuclear force and a strong nuclear force. The weak nuclear force is 10 raised to 31 times stronger than the gravitational force. And the strongest of all is the strong nuclear force, which is more than 10 raised to 38 times the force of gravity. So it is this positive nucleus, because of the protons, that attracts the electrons which are moving at a high speed, and they keep revolving around in different orbits around. And this gives the stable structure of the atom. If there are 10 protons, there will be 10 electrons in a variety of orbits. If there are 20 protons, there will be 20 electrons in a variety of orbits. And all this depends upon the way in which the electrons are organized. How fast do they move? How big is it? How small are things? Just to get an idea, let's talk of this. The electrons move around the nucleus at a speed of 2180 kilometers per second. It's quite fast. And what about the size itself? The size of these orbits, the smallest one of them, is approximately 1 angstrom, which is 10 raised to minus 10. 10 raised to minus 9 will break it down to 1 billionth. If we break that down also into 10 more parts, one part would be 1 angstrom unit of length. That's how small the whole thing is. And that's only the atom. Of course, depending upon the number of protons, the sizes would be slightly different depending upon the density and so forth. What about the nucleus itself? The nucleus is 10 raised to minus 15 meters. The atom is 10 raised to minus 10 meters. Nucleus is 1 Fermi. That's the unit that is called. That is 1 lakh or 100,000 times smaller than the atom. Seems very difficult to grasp. Please understand that if I have something like a small football placed here, and at about 100 kilometers from here, there is a ball bearing, and that ball bearing is going around this football, and that then is the size of the proton and the orbiting electron. And what about the material that is all in between? There's nothing. There's absolutely nothing. So in Indian philosophy, when they say that world is nothing but mithya, there's nothing around, that seems to be pretty true. And then this is the first orbit, and the next orbit is 4 times bigger, and the next orbit is 9 times bigger, and the next orbit is 16 times bigger, and so forth. So it means that most of the things are vacant. There's nothing in between. So I seem to be made of nothing. That's the nucleus in the center and nothing, empty space inside. Then why don't I just collapse and go right to the center of the earth? The reason is that electrostatic force. Realize two things. The orbit of the electron is extremely fast in such a small size, so it orbits 10 raised to 15 times per second. 10 raised to 15. 1 billion is 10 raised to 9. 1 trillion, that is 1000 billion, is 10 raised to 12. And another 1000 times more than that is 10 raised to 15. So around 6 into 10 raised to 15 hertz or revolutions per second. So many times the electron is going around. Two things will happen because of this. The electron will keep going around in all possible directions, and all of them will be going around. And all of them will have very strong forces between themselves and other electrons and other atoms and other molecules also. And these forces are extremely strong. So the whole thing then appears to be a solid material where nothing else can penetrate inside. And that is why when I bring my finger close and touch something, it is these electrons that are repelling each other. And so that gives us the feeling of pressure and so many other factors. And that's why we don't sink all the way down into the earth. Now, the next logical step. How many electrons are there? The inner electrons are quite tightly bound to the nucleus. But the outermost electrons are the ones that can interact with other substances. The outermost electrons have a special name. They are known as valence electrons. That is associated with valency, the way in which combinations take place. And among these valence electrons, some of the electrons are extra free. They can drift around here and there in metals. And these then are known as conduction electrons. So when a metal conducts electricity, it is these outermost electrons that flow from one side to the other. Rest of the material remains as it is. So electricity is nothing but the motion of those electrons. And what about the other structure that we talk of? If the outermost electrons, they have certain rules. They need to either have two of them outside to become stable or eight of them to become stable and so forth. It's part of chemistry. Let's not talk of that just now. Just know that either uh, they can become stable only if that number is a particular value, either 2 or 8. So there are two possibilities. The outermost electron, if there's only one of them, that particular element will try to give away that electron to somebody who is short of electron, and both of them will become stable. And once that happens, the two of them will get locked up together and they will form a molecule. Our most common molecule that we know of, salt, which is sodium chloride, is of this particular type. Sodium in its outermost shell has one electron, and chlorine in its outermost shell has only 7 electrons, so it is short of one electron. So the sodium gives away one of its electrons, and the chlorine accepts this electron, and chlorine is happy, sodium is happy, and they tightly bond to each other. And what we get is an electrostatic bond, which is the one of the strongest of bonds in sodium chloride. But there could be other situations where they don't actually transfer these electrons, but they share them commonly. So when two oxygen atoms come close to each other, they share their outermost electrons, each one completing in his own, and this becomes a covalent bond which forms the oxygen molecule. So same type, carbon will share its electrons with oxygen, two oxygen atoms, and each of them will become stable. That's how stability of materials takes place, and that's how compounds are formed, and all these bonds are formed. So we have metals, we have non-metals. All this is identified by those outermost electrons. And what about inside? Are there no properties associated with this? Yes, that's a completely separate area which we will discuss in detail, and we know of it. It's known as radioactivity. So all these outermost electrons have nothing to do with radioactivity. Radioactivity is associated only with the nucleus. But that's something that we will talk of much later. So all the compounds, all the colors, the rise in temperature, the shape, size, whether it's a gas, whether it's a solid, whether it's a liquid, whether whether it's a plasma or it's a Bose-Einstein condensate as the fourth state of matter and all that. Everything depends only on those outermost electrons. But of course, their behavior is controlled by the whole structure of the atom itself. But the nucleus is far away inside and pretty stable. So that's how atoms are and how that's how they behave. But there is one more factor. These electrons, as I said, are attached to the nucleus and they have a certain amount of energy that is required to pull them out. What is holding it is negative, and so that is known as the binding energy of the electrons. For a normal situation of one, I'll just give you a number. That's all. It's the electron is bound by minus 13.54 electron volt. So if I want to make it free, I have to pull this out. I have to provide that much amount of electron energy, and then the electron will become free. Now, if I go to the next orbit, it's already far away, so it needs less amount of energy, and the energy becomes one fourth. If it goes to the third orbit, the energy required will become one ninth. Next orbit, energy required will be 1/16th. So it is obvious by the time you go to about 5, 6, 7 orbits, then the amount of energy required is pretty low, very little. And so the electrons can very easily drift off. That also depends upon whether there are enough number of electrons or not. There is one more step, and that is that if I provide energy in some form, the electron will leave its particular orbit and go to the next level. It cannot remain there. So it comes down back to its normal state. It's like a person climbing up a staircase, going on top, finishing his job, and then coming down. Or a child climbing up and coming down the slide. So to go up, you need energy. And when it comes down, that excess energy is given out. If this excess energy is of a particular type, what the substance gives out is light. If that is a little less, what it gives out is heat radiation. And it can absorb energy by so many different methods. You can heat an object and then the electrons get excited. And that's what we see. And that's what I told you when I talked about the tungsten filament that gets hot. So when the element tungsten filament is heated by electricity, the electrons of the outermost shell get excited, go higher, they cannot go remain there, they come down, and in the process of coming down, they give out electromagnetic radiation in the visible range. What's this electromagnetic radiation? That's a big topic, and that to understand many things we will talk of next time. This then is the way in which light is given out. If the energy is a little less, then obviously it gives out heat energy. And the molecules have move and twist also, and they have their own energies. So all this results into a variety of forms of energy that are associated with atoms themselves. So heat energy, light energy is all associated with these transition of electrons and how the electrons move up and down. So the electrons can be shared, they can be transferred, they can rise and fall. And many of the phenomena of atoms and matter that we see around us is associated with these outermost electrons. But what about the nucleus? Something that I must clarify. For that, again, I'm going to talk of a few numbers because this is very interesting. The electron is extremely light. 9.1 into 10 raised to minus 31 kilograms. My God. Point 30 zeros, 91, so many kilograms is the mass of a electron, and around 1800 times heavier is the proton. And the proton and the neutron are practically the same. That is 1.67 into 10 raised to minus 24, 27 kilogram. That's the proton. And then because of that orbit, there is a particular size, and the next atom cannot go inside. So it's next, 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 and all these atoms come together. And how many are there? There was a scientist called Avogadro, and he came up with a particular number, very interesting number. 10 raised to its power is 10 raised to 23. 6.63 into 10 raised to 20. It's a very big number. And in 1 cubic centimeter, there are so many atoms that are present. So even if each one of them is 10 raised to minus 31 kg, all these atoms will result into quite a bit of weight. And that's what results into the mass that we know of. And how much mass is present per cubic centimeter or per cubic meter is the density that we know of. And what's the easiest way of keeping track of weights and densities? It's very easy actually. We are very lucky. By definition, 1 gram of water is 1 cubic centimeter, which means that if you take a 1 liter bottle, its weight is 1 kg. So density of water could be talked of as 1 kg per liter, or in technical terms, 1 gram per cc or 1000 kg per meter cube. That's what water is. And some things are very light. Air is about 1 kg per meter cube, 1000 times less. But what about that nucleus? If you remove the electrons, which we will talk of how sometime, and that's what happens in neutron stars and black holes. If you remove that, what you get is only the nucleus. And if you have only the nucleus and try to find out how dense or what is the weight of this, that's extremely high. It is known as neutronium. And this neutronium material is 2.3 into 10 raised to 14 grams per cc. That means 10 raised to 14 means 10 raised to 9 is 1 billion. 5 zeros more. That means 100,000 billion grams per cubic centimeter. That means so many times more heavy than water itself. So if you have a drop, forget drop, even a minutest particle of neutronium and you leave it, it's so dense it will sink right to the center of Earth. And a whole star made out of this is a neutron star. And at the core of a black hole is usually a neutron star. So you can imagine the amount of density of material that is there. These are all extremely heavy stuff. The whole sun, if converted to neutronium, could sink down to a very small size. So that's what neutronium is, not something that is commonly talked of. What we have to distinct ourselves is to atoms and their combinations, which is molecules. For a layman, this is all going to be complex. But for intelligent people like you and me, we need to know all this basic background of what atoms are in order to understand what light is, in order to understand what heat is, order to understand many other complex phenomena of how stars are formed and other materials are formed. If you have liked whatever I have said, please like and subscribe to this channel. Try and read up some information regarding all these atoms and so forth. It's fun. Keep this in mind. Forget the numbers. Understand how big or how small they are. And we'll use this information in our later concepts to understand many ideas like light and heat and magnetism and so forth. Till we meet again next time, beyond atoms. Namaskar.